Hello everyone, this is Dr. Venkatesh, Department of Physics, BVRA's Institute of Technology, Narsapur, and our course name is Applied Physics. And today I'm dealing the topic with magnetic properties. So magnetic properties of any materials we can learn here. This is the magnetic properties complete syllabus. Here we will learn the origin of the magnetic moment, definitions of the some fundamentals of magnetic materials, classification of the magnetic materials, and We's domain theory of ferromagnetism, hysteresis curve, soft and hard magnetic materials, magnetostriction as well as the magnetoresistance, and some applications we will learn here. So today we will discuss only the few parts of introduction as well as the origin of the magnetic moment with Bohr magneton, as well as the fundamentals, few more definitions and classification of the magnetic materials we will do here. So this is the entire syllabus and outline of the today's lecture. So now I will move for the magnetic materials introduction. So what are magnetic materials? So which is the fundamental question? We are receiving this question from the very lower levels also. So what are magnetic materials? So the magnetic materials that are attracted to the magnetic are called the magnetic materials. So the materials are attracted to the magnet are called the magnetic materials. So what are the uses of these magnetic materials? So there are a lot of applications we are using in magnetic materials. So first one is electric motors. So let you assume that any fan or any motor, so which is a completely application of the electricity as well as the magnetism. So here the electric motors we are using the coils. So inductor coil is the one of the major process in the electric motors. So and also magnetic data storages. So here magnetic recording media we will use DVDs, CDs as well as the pen drives, hard disks. We are using magnetic materials to store the data. So we know very well transport also we are using some magnetic materials. So recently nowadays we are using bullet train transport. So in the bullet train transport the principle and mechanism is the magnetic levitation. So this is the one type of application of the magnetic materials. So the magnetic levitation of the trains, which is approximately the bullet train speed is 600 km per hour. So the trains can be traveled. So and also we are using some magnetic materials in, we will use in the completely in biomedical applications. So here biomedical applications, medical applications, we will use as a MRI. So CT scan, we are using the magnetic materials. MRI is a magnetic resonance imaging. So which will give the tissue as well as the bone structure of the complete bone structure of the person. So we will use in medical everywhere. MRI also we are using, and industry we are using as a magnetic sensors. Magnetic sensors means in the form of in the name of we use as a semiconducting industry. So lot of semiconducting industries are completely in robotic in nature. So we'll use magnetic semiconductors, magnetic materials. So in the sensing applications. So here we are using nowadays we are using recording media as well as the sensing applications for the magnetic materials. So we know very well these are we are using for the entertainment purposes also. So speakers, so we are using magnetic material, as well as the earphones we are using the magnetic materials. So any more is there? So the list find out. Can you find out the list? So the list is continuously going there. So because here we are using a lot of applications for the magnetic materials. Now introduction. What are the examples of the magnetic materials? So what are the examples of the magnetic material? Tell me the few atoms. So that are the iron, as well as the cobalt, as well as the nickel, and you will take some transition elements, and the list is continuous. Only few, the list is continuous. What makes a magnetic material? If a material is a magnetic or not, non-magnetic. So that is the thing can be explained by the origin of the magnetic moment. Magnetism is a phenomena by which material exerts either attractive or repulsive force on another. So, and also the magnet is having the two poles. One is the north pole, another one is the south pole. So, the basic structure of the magnetic force is moment of electrically charged particles. Orbital motion and spin electrons and nuclear spin generate separate magnetic moments which contributes the magnetic behavior of the material. So here the orbital motion as well as the spin of electrons and nuclear spin, these are generates the magnetic moments. So this is the fundamental for the orbital motion as well as the nuclear spin and spin of the electrons. The spin of the electrons which will decide the magnetic nature of the material. So the way material responds to the structure and determines type of the material which will be identified by the orbital motion as well as the spin of an electron and nuclear spin is also. So why only electrons contribute magnetic field, magnetic moment? We know very well the electron is the negatively charged particle. Electron is a negatively charged particle, and this is a up and as well as the down state is there, up as well as down state. So the spin, the electron is completely revolved to the atom, so then the spin can be generated either up state as well as the down state. So we can take over the up state as well as the down state of the electron. So why only electrons contribute to magnetic moment? So the magnetic moment is due to spin of an electron is known as Bohr magneton. So which is the most important? So the magnetic moment is due to spin of electron is known as Bohr magneton. So here which is denoted by the mu b. The mu b is equal to QH by 4 pi me. So where the value of the Bohr magneton is 9.274 into 10 power minus 24 ampere meter square. So here the value of the Q is a charge of an electron. So the charge of electron is the 1.6 into 10 power minus 19 coulombs. And the H is the Planck's constant. So H value is, we know very well, 6.625 into 10 power minus 34 joule per Kelvin. And mass of the electron. So mass of the electron is Me is equal to 9.1 into, so 10 power minus 31 kg. So these are the fundamentals of Bohr magneton. So the Bohr magneton is the most fundamental for the magnetic moment. So here we are taking as a Bohr magneton. Let me erase. So where Bohr magneton, what is the Bohr magneton? The Bohr magneton, the magnetic moment due to spin of an electron. The magnetic moment due to spin of an electron is known as the Bohr magneton, which is denoted by the mu b. So this is the spinning completely. What about protons? Now electrons is okay. We are receiving the magnetic moment, Bohr magneton. What about protons? So proton is also having the mass. Same proton is also particle like an electron. But how we will receive the magnetic moment of due to a proton? So the mass of the proton is almost 1837 times greater than the mass of the an electron. So which means the magnetic moment due to proton is very less as compared to the electron. So as compared to the electron. So that means the magnetic moment due to proton is negligible compared to the electron. So we will consider only electrons magnetic moment. So next. The origin of the magnetic moment, which is completely depend upon the spin of the electron as well as the orbital moment of the electron as well as the total moment, total Bohr magnetons of the electrons. So here we will take as that which is also completely depend upon the electronic configuration of the material also. For example, let you take as a nickel. Nickel is having 28 atomic number. So we can write as configuration is 1s2, 2s2, 2p6, 3s2, 3p6 as well as the 4s2 and 3d8. So the d orbital is vacancy for 2 electrons, outermost 2 orbitals. So which means the nickel is having the Bohr magneton of the 2 mu b. Let you will take as iron an example. Iron is also ferromagnetic material, strongly magnetic material. So we'll take over. So its iron electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. So the d orbital is having the vacancy of the 4 electrons. 4 is completely empty. So one electron is vacancy is present in the d orbital of the iron atom. So which is having the 4 mu b Bohr magnetons. So similarly, if you write the calcium is having the atomic number is the 20. So which is completely filled. There is no vacancy for the d orbital, which is completely filled, or s orbital. S orbital is also completely filled. This means that the magnetic nature of the calcium is, so it is a non-magnetic nature. So that means the Bohr magnetons are the 0 mu b. Coming to the iron, already we have taken 26. This is a magnetic 4 mu b, and copper is having the 29 is the atomic number. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6 as well as the 4s1 and 3d10. One electron vacancy in s orbital. So one electron vacancy in s orbital vacancy. So here the magnetic nature of the copper is so very little bit as compared to this one iron. So the iron is ferromagnetic in nature, which is having a high. So the magnetic movement of different atoms we have seen. Now orbital motion of an electron. So electrons passing through a circular loop, or circular coil, so which produces the magnetic field like this. This is the orientation like this. So this can be produces magnetic field. As we know very well, according to the magnetism, so electromagnetism, we know very well the fundamental definition. Changing magnetic field produces the electric field. Similarly, changing electric field produces the magnetic field, vice versa. So electrons passing through the circular loop coil, then that can be produces the magnetic field. So similarly, electron is, when you will consider one hydrogen atom, the electron is revolving to the nucleus, so which is also produces the spin. So the electron revolving the orbital, that is also produces the magnetic field. So then the total magnetic moment is defined as, which is equal to the combination of the orbital magnetic moment plus as well as the spin magnetic moment. So the total magnetic moment of atom is considered as orbital magnetic momentum plus spin magnetic momentum. So here the basic fundamental definitions we can see. So that is the origin of the completely magnetism we have seen. Now we'll go for the basic definitions of the magnetism. So here some fundamental, the concept of the magnetic poles. So the poles are fictitious. So the points near the end of the magnet where the one might consider all the magnetic forces on the magnet to be concentrated. So which means the pole strength, the magnet is completely dependent upon the pole strength of the material. So the pole strength of the magnet is very high. That means the attractive power or repulsive power is very high at poles, and at the center it is very low. The magnetic dipole moment. A dipole consisting of the two magnetic poles of opposite polarity and equal strength separated by the small distance. So this is a dipole, either positive charge and negative charge. So small distance, they are separated by the small distance, is known as the dipole. Magnetic dipole means a dipole consisting of the magnetic poles of the opposite polarity and equal strength separated by a small distance. And magnetic dipole moment. So isolated magnetic poles have never seen in the nature, but occurs isolated pairs. One pole being positive and another is negative. Such pair is known as dipole. Isolated magnetic poles are never in the nature. We are not seen in the nature. So the magnet is always having the two poles. One is the north pole, another one is the south pole. So the magnetic magnetic moment of dipole is defined as the m is equal to p into l, pole into l. So which units is the ampere meter square. So isolated magnetic field never existed, which is the formula del dot v is equal to 0. So which is the Gauss law in magnetism. A magnetic field. What is magnetic field? The field means the magnetic field is the area around by a magnet in which there is a magnetic force is there, similar to the electric field. So the area is surrounded by an electric charge is known as electric field. Here also the magnetic field is the area surrounded by a magnet in which there is magnetic force is known as magnetic field, which is denoted by the H. So the units for the magnetic field is the ampere meter. And magnetization. So what is called the magnetization or intensity of magnetization or magnetic intensity are same. So magnetization means the magnetic moment per unit volume is known as the magnetization of the material. So which is denoted by the m, and m is equal to small m by v, magnetic moment per unit volume. So these also having the units ampere per meter. So here the process of converting non-magnetic sample to magnetic sample we can do here. So that is the help of the magnetization. The magnetization for non-magnetic sample, the random spin orientations we can see. That means the spin orientations are in the random in nature, very zigzag in nature. So which means m is equal to 0. There is no net magnetic momentum. So which means the magnetization is 0. So coming to this 1 second, so the magnetic field aligned spins rotating towards the direction. If you are applying little bit spin, so the direction of the dipoles, whatever the direction of the spin alignment is, so towards the magnetic field, it can be changed to the magnetic field, which means the m is not equal to 0, the magnetization not equal to 0 in the second case. Coming to the third case, we are applying more and more high fields. The magnetization m is not equal to 0. M will receive the maximum value. So all spins in the direction of the magnetic field sample can be magnetized. The magnetic sample m is not equal to 0, which means m is equal to maximum value we will receive. M is equal to maximum value we will receive. So it's a poll question. What is the net magnetic moment if all the dipoles are in the random direction? As you know, you already seen a random direction, net magnetic moment is 0. So that's why we'll take as option A is the right. And magnetic induction. What is induction? A flux, magnetic flux density. Magnetic induction or magnetic flux density. So magnetic flux density in any material is the number of magnetic lines passing through the unit area. Generally, flux is denoted by the number of if you say that is electrical flux, number of electrical lines passing through the unit area is known as electrical flux. Similar to the number of magnetic lines passing through the unit area is known as magnetic flux, or else it is known as magnetic induction. So which is denoted by the B. So the units for the magnetic induction are the Tesla. So the magnetic induction B is equal to mu naught into H plus M. So where B is the magnetic induction and mu naught is the permeability of the free space and H is the magnetic field plus and M is the magnetization. So here, for example, the material is non-magnetic material. You are applying the magnetic field H to the non-magnetic material. The magnetization M becomes to 0. That means that is a non-magnetic material. So that's why B is equal to magnetic induction B is equal to mu naught into H only. Because here the M is 0. We can substitute M here. Then we will receive B magnetic induction which is equal to mu naught into H. So similar, if the material is a magnetic material, so you are applying the magnetic field to the magnetic material. So where M is not equal to 0, that means B is equal to mu naught into H plus M. B is equal to mu naught into H plus M. What is H? Magnetic field. What is M? Magnetization. So this is the, what is mu naught? Permeability of free space. And what is B? Magnetic field induction. So susceptibility, next thing is the fundamental susceptibility. It is defined as a ratio between the intensity of magnetization versus magnetic field. Intensity of magnetization versus magnetic field is known as susceptibility of the material. So which is also most important. The susceptibility value is positive, one type of magnetic material will receive. Susceptibility of the value is negative, one type of magnetic property will receive. Susceptibility is small, susceptibility is high. We can see the classification of the magnetic materials later. So the units for the susceptibility is nothing. So because here no units. Already M is having the same units and H is having the same units. So Xi magnetic susceptibility is not having the any units. The permeability. So it is defined the ratio of magnetic induction in the sample to the magnetic field intensity. So mu is equal to B by H, where B is the magnetic induction and H is the magnetic field. So mu is equal to B by H. What is the relative permeability? The ratio of the permeability of a specific medium to the permeability of the free space. So permeability of the specific medium by the permeability of the free space is known as the magnetic relative permeability. So the units of the magnetic relative permeability, it is not having the any units, because the magnetic specific medium permeability having the unit, no unit. So this is not having the units. So which is denoted by the mu r. Mu r is equal to mu by mu naught. So and one more thing is there. So the relationship between the Xi and mu r. What is Xi? Xi is a susceptibility and mu r is a relative permeability. The relationship between these two we can find here. So B is equal to, we know very well. What is B? B is equal to magnetic induction, which is equal to mu naught into H plus M. According to the previous definition, B is equal to, we can take over mu naught into H plus M. Here I expanded. So next, and we know very well Xi is equal to susceptibility is equal to M by H, and Xi is equal to M by H. So M we can written as, from this M we can written as this. So M we can written as Xi into H. Now I will substitute the value of the M value in magnetic induction. Then we will receive, we can rewritten as B is equal to mu naught H plus mu naught into Xi H. Xi H value. From here, what are the common values? The common values are mu naught as well as the H. So now I can take over the common of these values and I will rewrite as B is equal to mu naught into 1 plus Xi into H. But since we know very well the magnetic induction B is equal to mu into H, that means the permeability mu value is equal to B by H. So we will take as mu B is equal to mu into H. So now I will substitute this B value and I will rewrite as a B value here. So BH is equal to, we can written as B mu H is equal to, that implies mu H is equal to mu naught into 1 plus Xi into H. So here HH get cancelled and we will take over mu H value. So mu H value means mu is equal to mu naught into 1 plus Xi value we will receive. So now I will add this. So mu is equal to mu naught into 1 plus Xi. This means mu by mu naught is equal to, you can send the mu naught to the left side, and mu by mu naught is equal to 1 plus Xi. The mu by mu naught value is known as relative permeability mu r, which is equal to mu by mu naught. So mu by mu naught is equal to mu r. Mu r is equal to 1 plus Xi. So which means the relationship between the magnetic susceptibility as well as the relative permeability is the one the constant is the one variation is there. 1 plus Xi is equal to mu r, which is the relationship between the Xi as well as the mu r. So the magnetic materials fundamentals we have seen up to here, and up to here we have seen the fundamentals and origin of the magnetic moment, Bohr magnetic moment, as Bohr magneton, as well as the some fundamentals we have seen. And next we are moving towards the magnetic materials classification. So the magnetic materials can be classified into different types. So simply the material attract or repel to the magnetic materials, we can decide the classification of the magnetic materials. The material repels, so we can say that material is a diamagnetic material. The material is attracts to the magnet, attracted by the magnet. We can say that is a paramagnetic or ferromagnetic material. The attraction is very weak, little bit weak. So we can say that is paramagnetic material. The attractive force is very strong in nature. So that is known as the ferromagnetic material. So these are the classification in general view. So atomic view of the classifications of the magnetic materials. So the permanent dipoles, we'll talk about the permanent dipoles. The material which is having the permanent dipoles, we can say that is paramagnetic as well as the diamagnetic material. There is no permanent dipoles, we can say that is a diamagnetic material. So the permanent dipoles is present in the material, we can say that is a paramagnetic and ferromagnetic material, which is completely depend upon the spin-spin interaction of the electrons. So if the spin-spin interaction is presented, we can say that is ferro. Spin-spin interaction is not presented, say we can say that is a paramagnetic material. So spin-spin interaction is presented, we can say that is a ferromagnetic material, antiferromagnetic material and ferrimagnetic material. Again the classification of the ferro family. So alignment of the spin and magnitude, which is the same and equal. Alignment of the spin as well as the magnitude, both are equal, same and equal. We can say that is a ferromagnetic material. So the alignment of the spins and as well as the magnitude, both one is spin is opposite and magnitude is equal. So we can say that is a antiferromagnetic material. So both are different. That means alignment of the spins and magnitudes opposite and equal respectively. Then we can say that is a ferrimagnetic material. This is the atomic point of view. So the classification of the magnetic material. This is the main classification of the magnetic material. Here we will discuss these types: diamagnetism, paramagnetism, diamagnetic materials, paramagnetic materials, ferromagnetic materials. Ferro family that can be classified into again three types: ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. So coming to the first one, the diamagnetic materials. So the materials which are repelled by the magnets. The materials which are repelled by the magnets are known as the diamagnetic materials. See here the diagram. So the materials are repelling in nature. So they are repelling. So atoms with no permanent dipoles, because the electrons are completely filled with the orbitals. Let you will take as example as a previous we have taken. Calcium we have taken previous. So similarly you will take as a zinc. Zinc is having the atomic number 30. That means which is completely filled with the electrons. There is no vacancy for the orbitals. So these are atoms with no permanent dipoles. These which is having the negative susceptibility. So the atoms having the negative susceptibility. So and independent of temperature and strength of the field. If you are applying temperature to the diamagnetic material, so which is independent nature we can see here. We are applying the temperature, that is similar nature only we can see. We are applying the magnetic field, so similar nature only we can see. There is no change in the magnetic field as magnetic nature. There is no change in the magnetic nature with respect to temperature, with respect to applied field. So this is the Xi value. Xi is almost constant for the diamagnetic materials. No spin alignment we can see. The examples for the diamagnetic materials are bismuth, antimony, copper, silver, gold, water. A lot of materials we are seeing. They are repelled by the magnetic field, magnets. So they are the materials repelled by the magnets are known as the diamagnetic materials. Coming to the paramagnetic materials, so they are attracted, the materials which are attracted by the weakly, the attraction is weakly attracted by the magnets. The weak attraction by the magnet is known as paramagnetic substance. If you see the diagram, the materials is attracting the magnetic lines. So which is having the atoms having the permanent dipoles. As I told you previous, copper example for the paramagnetic nature. So paramagnetic nature is attracted but very weaker attraction as compared than the ferromagnetic nature. Small, the susceptibility value is the small as well as the positive value here. There is a negative value we have seen in the diamagnetism. Here the susceptibility value is the positive and which is the small. So which is also inversely proportional to the temperature. That means we are increasing the temperature, the susceptibility value will be decreased. If you are decreasing the temperature, susceptibility value enhancement we can see. So it is completely inversely proportional to the temperature. And the magnetization, if you are applying the magnetic field to the paramagnetic substances, so the magnetic field linearly increases. Linearly you are increasing. So the magnetization value is also linearly increased. The magnetization increases linearly with respect to the magnetic field. So we can see in the diamagnetism there is no increment, there is no change in the magnetic field as well as the temperature susceptibility values, there is no change. But here the little bit changes we can see here. The spin alignment here in the random direction. So for example, the applied magnetic field is absent. If you see the diagram, so this is the spin alignment in the random in the direction. If you are applying the magnetic field, so it is automatically the field is present, the spin alignment in the one direction only, completely towards the magnetic field. So which is the major difference between the diamagnetic as well as the paramagnetic also. The examples for the paramagnetic materials are lithium, sodium, aluminum, manganese. So these are the best examples for the paramagnetic substances. Next one is the ferromagnetic materials. In the classification of the magnetic materials, ferromagnetic materials, the materials are attracted by the magnets very, very strongly in nature. So if you see the diagram, you can see. So these are attracted very, very strong in nature. So the atoms is having the permanent dipoles. So as we have seen in the last time example in the magnetic orientation, we have seen there, that is iron we have seen. There is a 4 mu B value we have seen, 4 Bohr magnetic values is there. So that is having the highest. So that means the iron is having the more attractive nature as compared with the copper and calcium. So these are large and positive susceptibility values can be present in the ferromagnetic materials. The susceptibility is always positive and which is a large value we can see. The susceptibility is inversely proportional to the temperature and follows the Curie's law. That means if you are increasing the temperature, the susceptibility will be decreases. So and also follow the Curie's law. What is Curie's law? So which means that at Curie temperature, the ferromagnetic material, particular temperature, ferromagnetic material becomes to the paramagnetic substance. That particular temperature is known as Curie temperature. So when you are applying an temperature to the ferromagnetic material, so the ferromagnetic material transition into the paramagnetic substances at particular temperature only. That particular temperature, this is a TC. That particular temperature is known as the Curie temperature. So here also we can see as similar to the in the paramagnetic nature. The magnetization is lacks applied magnetic field and forms the hysteresis loop. So the BH curve can be generated. So generally when you are applying the magnetic field to the magnetic material, the material can be magnetized to up to absence of the particular time also, that can be showing the magnetization. So the magnetization value, whatever the highest value is there, so that is the saturation magnetization value. And the width of the loop can be decided the coercivity, which will decide the hard and soft nature of the magnetic materials. Hard and soft nature of the magnetic materials. The width of the loop is very high, that material is in the very, very hard nature. So the loop is very low, soft nature we can see. So it will decide the hard and softness of the magnetic materials. And height of the loop will be denoted by the retentivity of the magnetic material. These things we can see in next class. So spontaneous polarization is also present in the ferromagnetic materials, and the spin alignment is randomly, we can see in the spin alignment is the randomly and but one orderly. That means so completely in the domains, like your domains we can see. So if you see one domain, the spin alignment is one direction only completely. So if you are applying the magnetic field, definitely these can be aligned into only one direction. So this is a major difference between the paramagnetic as well as the diamagnetic as well as the ferromagnetic. So the spin arrangement is in the random in nature there, paramagnetic completely. The spin arrangement is also random, but in the domains are the random in the ferromagnetic materials. The examples for the ferromagnetic materials are iron, nickel, cobalt, gadolinium, and rare earth elements we are seeing always. So iron we have done in the previous slide. So anti-ferromagnetic materials. What are these? These are also subclass of the ferromagnetic material. So the spin alignment is anti-parallel in neighboring atoms with equal magnitude. If you see the diagram, the anti-parallel spins here represented, and in neighboring atoms with the equal magnitudes. So this is the major difference between the ferromagnetic material and anti-ferromagnetic material. Remaining same. Susceptibility is also small value, but positive value here we will receive. And after Niels temperature, the material is in the paramagnetic state. What is Niels temperature? So when we are applying the temperature to the antiferromagnetic material, so after particular temperature, the antiferromagnetic material becomes to paramagnetic state. So which is known as, at that particular temperature, we can say that is known as Niels temperature. While previous we have done in the Curie temperature, ferro to para substance is known as Curie temperature, anti-ferro to para substance is known as Niels temperature. The examples for the antiferromagnetic materials are chromium, iron manganese alloys, and nickel oxides. If you see the diagram, we are applying the temperature to the magnetic material, so antiferromagnetic material. So its magnetization is initially increased up to particular one point, and later that, so that can be decreased. So that can be decreased in nature, we have seen. So we have seen the decrease in nature. So this temperature is known as, whatever the temperature, this temperature is known as Niels temperature of the material. What about ferrimagnetic material? So classification of the magnetic material, and last thing is the ferrimagnetic material. So these are the subclass of the ferromagnetic materials, and also spin alignment is anti-parallel in neighboring atoms with the unequal magnitudes. There also we have seen the antiferromagnetism equal magnitudes, but here the unequal magnitudes we can see. The spin alignment in is anti-parallel in neighboring atoms with unequal magnitudes. The susceptibility value is the same, small and positive. After Niels temperature, this is also showing the paramagnetic nature. So examples for the ferrimagnetic materials are the ferrites. So the ferrites are the most important magnetic materials. Recently, nowadays, we are using the ferrites for memory as well as the sensor applications. Even though we are using in the electrical fans also, we are using the ferrite cores, and everywhere motors also we are using the ferrite cores. So these are the inductor applications we are using the ferrites. Ferrites are also classified into the ferrimagnetic materials, which means which is having the metal oxide as well as the iron oxide present in the ferrites. The combination of the metal to iron oxide into the 1:2 ratio is there. So these are the most important magnetic materials for the several applications. So here also ferromagnetic region is there when we are applying the temperature to the ferrimagnetic materials. So its magnetization can be like this. So if you are applying temperature, so its state can be changed into this way. So paramagnetic state, anti-ferro to para, ferri to para. So this is known as Niels temperature. So this particular temperature. So these susceptibility values, this can be explained by the completely on the Curie's theory, and we can do in the next class. Now, thank you.
Like, share and subscribe. Hit the bell icon for more updates.